Hi everybody, welcome back to the channel. In this video we are going to take a look at something that we're not going to see a lot of in this course, in a Calculus 1 course, but it is good to take a look at. Whenever you work through some kind of new idea in math, it's pretty often that at some point you'll kind of need to turn around and work through that idea backwards and try to go the other direction. And so in this section I'm going to talk about something that many of you might need down the line, down in your future sometime, but something that you may have heard of before called differential equations. Okay, and so what a differential equation is basically an equation that starts out with not just a function y, but also maybe there's a y prime that starts out in the equation, or sometimes even a y double prime, or they can get pretty complicated. But the idea is if you start out with a y or a y prime or a y double prime in your equation, can you figure out what the function y is supposed to look like that satisfies that equation, or that makes it a true equation? Okay, and so we're going to kind of build this up a little bit. We're going to see kind of where we're going to go with this. I won't try to give away the whole story yet, but let's go ahead and kind of start out by looking at the kind of the most basic type of differential equation that you could start out with or come up with, or at least one of them. And so let's say we have something like this. We could even go pretty simple. What if I told you that y prime is equal to c, which is just a constant? I think you'd be able to come up with that one fairly easily. And if I said, well, what is y that satisfies that, such that its derivative is equal to a constant? Well, you'd probably be able to come up with, well, that's c times x. That's going to be something that's linear. That probably makes sense, because if you take y prime, you just get y prime equals c there. So that's probably the easiest case. Let's look at one that's still pretty easy, but a little bit more difficult than just looking at a linear case. And that's what we're going to focus on in this section. Is what about this example that has something like y prime equals, I'm going to call it k times y. So not just k or not just c as a constant, but some constant k times y. And so what we're going to try to do is come up with an example of a function y that's going to satisfy this equation, that's going to make this equation true. Okay, so I don't know if you have any intuitive thoughts about kind of what you should try first, or what kinds of functions you could use where you'd say, well, how do I even try to plug this in? Let's just try, for an example, try to just pick a random y value and see if that's going to work. Now that's probably not going to work if I just kind of grab one. But let's just use something like does that work if y is equal to x squared? Okay, here's what that would look like in order for that to try to, in order for us to try to kind of figure out whether this is going to work or not. Go ahead and find y prime. That's 2x. Plug in y where you see a y in the equation. Plug in y prime where you see a y prime in the equation. Do you get a true equation or not? Okay, hint, with this one, no you don't. Okay, but try it anyways. Let's go ahead and plug in. So where you have a y prime, you're going to replace that with a 2x. And then you have a k, and where you have a y, you're going to place that with an x squared. So is this a true equation? Not for all x, it's not. Now, could you find a specific value of x for where that makes this work? Yes, but we're trying to make it a true equation, which means it works for every value of x. Okay, so x squared is probably not the equation that we want to be looking for. In fact, pick any power, pick any polynomial over here, and I could just call it something like x to the n. And we know enough about polynomials for us to kind of talk in vague terms over here, but x to the n, and if you take the derivative of that, you get something like n times x to the n minus 1, and you're always going to be off by a power of 1. Let's try to do the same thing we just did by plugging those in. Go ahead and plug in for y prime. You get n times, so n times x raised to the n minus 1 equals k times, let's see, what was y again? That was x to the n. Is there any way that x to the n is equal to something that has an x to the n minus 1 in it? No, there's not. So there's no way for this to work really with any polynomial or any, any degree. It doesn't really matter. And so if you're trying to make this equation over here on the left work that we're starting with, really the question is, what function do I need that almost kind of gets you itself? Because we have a y prime in here when you take the derivative. So we have a y prime in here, we have a y in here, and you should almost think about that like you have the same, I don't know, it's not really a degree if it's not a polynomial, but the kind of the same type of function on both sides. Okay, I'll tell you, trig functions get us close, but not exactly the same, because if you have the trig function over here, maybe you have a sine function as your y, then y prime is not going to have a sine function in it. It is going to have a cosine function in it. So you're kind of close. You still get a trig function over there, but it's not going to be exactly equal. That's actually a good strategy down the road, maybe in a future class, when you see stuff that has a y double prime in it, and you could think about using that with trig functions because they tend to kind of repeat themselves every second derivative in there. Okay, so let's see if we can kind of come up with a value of y, or a function for y, that's going to make this work. What we just said is that polynomials don't really work, trig functions don't really work. Maybe a good thought then is, I wonder what about exponential functions. Okay, pick your favorite exponential function. My guess is you're thinking about e to the x, because we like that one a lot, because e to the x is its own derivative. And so does e to the x work? We could try this and see if this one's going to work. Let's go ahead and plug in for y and plug in for y prime again, just like we did earlier. Now what we have is e to the x is equal to k times e to the x. We are really close. We're off by this factor of k in here. Okay, and so the way that we're going to kind of account for that, because we do get something really close to this, the way we're going to account for that is by throwing another function up in the exponent. So you're going to have a chain rule in there that's going to kind of kick that k to the front. Okay, so for example, let's say, again, we're trying to solve this differential equation right here. We're trying to figure out which function of y is going to make this equation true. Let's modify just a little bit. Instead of y equals e to the x, what about now if we have a chain rule where you have to multiply by the derivative of the inside, you have to multiply by the derivative of the exponent there. If we have a k up in the exponent with the x, then when we take the derivative of that, we need something like y prime is equal to e to the kx times k, because you need the derivative of the inside there. And now when you replace a y, you get k e to the x on the right side, and when you plug in for y prime, now you get a k e to the kx. Or I should say, on the right side, it's not actually an e to the x, it's an e to the kx, because that's what y was. And then on the left side, you also get a k times e to the kx as well. So ding, 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 we kind of have a winner here, that this is what we want right there. Now, we can actually go one step further and just add an extra little piece in here, because if you have a function that's y equals k raised to the kx power like this, you may remember that, let's say we have a coefficient out front. Okay, I'll just call it a, I guess. So if you have an a value out front, what's going to happen when you take y prime is you're actually still going to have that a down in front. It's going to end up being a times k times e to the kx. So if you multiply by a out front in your y, you actually pick up that extra a out front in your y prime as well. So that just even makes it a little bit more generic of an example that's going to work in order to solve this differential equation up here. Okay, so not only do we want e to the kx, what we actually want is even a little more generic than that. We want an a out front and have y equals a times e to the kx, like that. Okay, so by the way, a, if you think about what happens, like what's this a doing right here, and you can think back to when you dealt with exponential functions in your past. When x is 0, y equals a, we would call that our y-intercept. So basically this a value here is a y-intercept, or another way to talk about it as a y-intercept is to call it y of 0. Okay, so let me write it like this. This is kind of your first example, probably for all of you, for at least most of you in your life, of solving an example of a differential equation. Congratulations, it's your first time for everything. Okay, so let's start with, so here's kind of the summary of what we just said. If we start out with something where we know how y prime behaves, and we know that y prime is equal to k times y, then what we have is that we know exactly what that function y is supposed to look like. We know that y is supposed to look like y of 0, which we called a, but you could, to use the specific function value there, you could call it y of 0, times e to the kx. Or sometimes some of our examples when we deal with exponential examples are going to have t as your input, so you could put a t up there instead of an x if that's your input variable. Okay. So you might be asking, well, why do we care about this? Why are we talking about it solving a differential equation? Well, sometimes we know how a function's derivative behaves, or you might say we know a speed or a velocity. And you may have heard this phrase before, but when we talk about this equation up here about how y prime and y relate to each other, there's a couple of phrases we often use. One of them is to say that y prime and y are directly proportional, okay, or directly related to each other. And so if you ever hear this phrase, especially in kind of problems involving this section, but if you hear that two quantities are directly proportional, this might be a good thing for you to think about, is that, oh, it's actually saying that we're starting with this. And right when you start with that, you can go down here and say, oh, I know exactly what y should look like. Okay, so a lot of the problems, I'll tell you, a lot of the problems involve an equation like this down here, and that's not really going to involve a lot of new calculus for you. That's going to involve exponential functions and solving an exponential function using logarithms, and talking about exponential growth and decay. You've seen a lot of that in your past already. So I will say that out of the problems that you're going to see, not a lot of them are all that new and different. They really are solved in a lot of the same ways you've seen in your past. It's just we're involving this new idea of solving a differential equation, saying if you know how y prime behaves, then you can know exactly what y is going to look like.